If not, then you may write a message. So today is the first class of Thermodynamics 1, and this is fall semester 2020. Right. So ये अपने mics off कर दें, किसी का mic on है I think. Okay, so this is a core course of mechanical engineering. It is 3 credit hour course and there will be 2 sessions per week, but now the classes are split into further 2 groups. So there will be 4 sections from these 2 sections, right? So total session duration is 3 hours, right? So there will be 2-hour class and then there will be 1-hour class. Okay. So I welcome you all to the third semester of your BS Mechanical Engineering. In this semester, you will study some of the very core courses of mechanical engineering, which mainly includes thermodynamics, fluid mechanics, and mechanics of materials. So these are the foundation courses of mechanical engineering. Right, so far you have studied many courses which were kind of generalized courses, right, in your first 2 semesters, except a few ones which were very related to mechanical engineering, right? So I would like to highlight the importance of the study of thermodynamics in mechanical engineering, right? So actually in industry, there is no process that executed within these industries where there are no transfers of energy. You see a graph on the screen here. So what this graph is telling you, it is data from 2018. It represents the world electricity generation, which is about 26,700 terawatt hours, right? So this is from this source. And what you see from this diagram, that the total amount of electricity which is produced all over the world, major portion is actually being produced using coal, about 38%, then gas, about 23%, right? Then there are oil, 3%. So you may see here the more than 50% of the electricity all over the world is produced from these sources, from fossil fuels, which is coal, gas, and oil, right? The remaining is from hydro, nuclear, and solar and wind. So a major portion is still being produced using that fossil fuel sources. So all these fossil fuel sources, how they are producing electricity. So actually what you are doing here, you are converting the chemical energy of those fossil fuels into thermal energy first. So this thermal energy is then converted into mechanical energy. And this mechanical energy is then converted into electrical energy. So electrical energy, which we use in our daily lives, is not present, is not naturally available to us. We have to produce this electrical energy from some other sources of energy. So, and most of those sources of energy are still based on fossil fuels. So this is the science. Thermodynamics is actually dealing with this science to convert this energy from one source to another source, which involves the thermal part in it. Because in all these sources, coal, gas, oil, even in nuclear, and in some cases, solar energy, what you are doing in all these cases, coal, gas, nuclear, solar, and oil, you are converting one form of energy, which could be chemical form of energy in case of coal, gas, and oil. And in case of solar, it is the radiation, electromagnetic waves. So first you convert all these energy into heat, and then this heat is converted into mechanical energy. Or mechanical energy means when something is moving. Something is moving either in rotary path or in the linear path. Some object is moving. So you are producing this movement from the energy of these sources. And this movement is then converted into electrical energy using Faraday's law of electromagnetic induction. So It means, so this is the science, this thermodynamics is actually telling us that how this energy from these different sources can be converted into electrical energy. So electrical energy, unfortunately, is not present naturally. We must need to produce this energy. And as mechanical engineers, you are the ones who are actually producing this energy. After that, it is the work of electrical engineers to deal with this electrical energy. But how this electrical energy will be produced? It is from some energy conversion process. And thermodynamics simply is the science which is telling us how you can convert this energy from one form into another form in the efficient way. Okay, I exit the full screen. I just want to see if everyone is still with me. Right, people are still trying to join. For example, this Tariq Khan outside High Tech University, it means he is not joining the class using High Tech ID, so that's why I'm denying it. So everyone is on board. If are you hearing me correctly? So please, Sia, please confirm me again. Is screen visible to all? Please write a message so that I continue. Okay. Right. Okay, I switch back. All right, so let's continue our discussion. So I am Abdul Wahid Badr. So you all would know me from your seniors. So you can get the proper introduction from your seniors. We shall have a proper face-to-face introduction once we will have face-to-face classes in High Tech University from third week probably. So the office number is ME03. Discussion hours in this semester is from 9 to 12 hours. On every Thursday for this semester. If you cannot understand something in this class, in the online class or in the face-to-face class in the high-tech university, then you may come to me for discussion about any topic, right? Or if you want to meet me outside these hours, then you can write me an email. Okay, so we shall have a proper introduction later on when we'll be facing each other in High Tech University. So this course, Thermodynamics 1, this course code is not correct. I think it is 102. Okay, so here are the recommended books which we shall be following in this course. This first book, Thermodynamics by Sengel, 8th edition, is the main book. Majority of the course will be covered from this book of Sengel and Bowles, right? The other books are just for references. Some part is covered from these other books too, right? So we shall be using these three books also in some cases where something is not very clear from this book for any particular concept, right? So here is the course outline of this course, right? So here you see 8 chapters actually. So these are just the names of 8 chapters which we will try to cover in this course. The detailed course contents of these chapters are available in the lesson plan, which I have already shared in the Google Classroom, right? So today we shall start this first chapter, Fundamental Concepts of Thermodynamics. Most of these concepts you have already studied in the basic course of engineering physics and also in your FSC and metric physics. Those will be again repeated, and I am very much sure many of those concepts are still not clear to you. So we shall clear those basic concepts again in this course. Right. Then the second chapter is about energy, energy transfer, and general energy analysis. The purpose of this chapter is to introduce the first law of thermodynamics, which you have already studied somewhere. But again, I'm telling you that the portion which you have studied before in FSC or in metric, I'm very much sure that the core concept, most of you, is not clear. So we will clarify the core concept of first law of thermodynamics in this chapter. In the second chapter, then properties of substances. This is the most important chapter of thermodynamics 1. Without this chapter 3, you cannot understand thermodynamics 2. You will have difficulties in the course of power plants. You will have huge difficulties in the course of refrigeration and air conditioning. So all those advanced subjects, they are dependent upon this chapter 3. So this is the most important chapter of all these. Okay, then chapter 4, energy analysis of closed systems, and chapter 5 is energy analysis of steady flow systems, which is also known as open systems. So these two chapters are also actually the continuation of chapter 2. So actually in these two chapters, we shall be dealing with the application of first law of thermodynamics. Here we will just define first law of thermodynamics and many of its forms. Many of its forms means many mathematical forms of this first law of thermodynamics. Then we shall be applying this forms, various forms of thermodynamics in these two chapters. So these are practical application of first law of thermodynamics. Then chapter 6 will be about second law of thermodynamics and its applications. Then chapter 7, the most confusing concept in thermodynamics, and that is called entropy, but it is very important concept. Without this concept, we cannot solve many practical problems, right? So this is also very important chapter, entropy. Then there is gas power cycles, the chapter 8. This is also a practical application of whatever you have learned in the first 7 chapters. Those will be applied in these practical application. This is a pure practical application in which we shall learn about diesel cycle, Otto cycle, and many other cycles. But normally we left with very little time to cover this chapter 8. So first 7 chapters are very important. Without these chapters, you won't be able to understand chapter 8 and the thermodynamics 2, which is totally an application based subject, which you will study in the next semester. Okay, so I exit again and just to see if everyone is with me. So this person, XP Wiki, is trying to join, but outside High Tech University. That's why I have to deny the entry. Right, so once again, everyone is with me. Please write a simple message here. Right, okay, thank you. Okay, so here is the probable grading policy which we shall be following. Quizzes and assignments, most probably it is of 10% weightage, session 1 exam, 15% sessional 2, 15% projects and presentations, about 10%, and final exam 50%. But those are still subjected to change, right? So they may change. This is just a probable grading policy which we shall follow in this course. If you keep the proper discipline in the online class and also in the university classes, then this is the least concern to me. This gradings and exams, quizzes, this is of least concern to me until you maintain a proper class discipline, right? Then these are not important. You will get very easy quizzes, easy sessional exams, and very easy final exams, right? Until and unless you cooperate with me in the class as far as the discipline is concerned, then this is not important. The important thing is to transfer the knowledge in the most efficient way, right? Okay, so let's move forward. So now, today we shall start chapter 1, fundamental concepts of thermodynamics. Normally in the first class, I give a different type of lecture, but that is not possible in the online class. Once we shall meet in the face-to-face class, then we shall have some other important discussion before the start of this course. But now, because in the online class it is not possible, so I will just start chapter 1 from today, which is about the fundamental concepts of thermodynamics. This chapter is mainly covered from this book, Thermodynamics by Sengel, as I already told you. Now we shall be following 8th edition. So there is no need of 5th edition anymore. So 8th edition is easily available online. I have already shared in the Google Classroom also. So these are the other 2 important books. I will share those books, the soft copies, in the Google Classroom also. Right. So let's start our lecture or chapter 1. So this is about thermodynamics and energy. Thermodynamics is a subject which is actually dealing with energy, because every living thing actually that depends upon energy for survival. Without energy, we cannot survive simply. And as our living standards are increasing day by day, where our dependence on energy is also increasing with every passing day. For example, now we are using these laptops to communicate with each other, but without electrical energy, those cannot run. We cannot listen to each other. We cannot have a direct communication if there is no energy. In the rooms where you are sitting, all of you, there must be some fans running, lights are switched on, refrigerator and air conditioners are running, right? So all these devices in our surroundings, our mobile phones, everything which you can imagine, it needs energy to run it, right? So it means the most important thing is to have this electrical energy in our useful form. And our useful form of energy, in most cases, is electrical energy, right? Because most of our devices, without them, we cannot even, wait a minute. So all of these devices, without which we cannot imagine our lives nowadays, those are running on energy. And most of them are running on electrical energy. But there are some other forms of energies. For example, our automobile is running not on electrical energy, but it requires mechanical energy to run. So in most of the cases, the useful form of energy for us is electrical or mechanical, right? So most of our devices, they are running on electrical energy, or many are running on mechanical energy. And I already told you all these energies needs to be transferred from one form to another form, because our useful form of energy is not present naturally. So we have to convert one form of energy into another form of energy. Right. So that's what I have explained. So let me go. So energy, we know it exists in many different forms. For example, energies are locked in the atoms of matter, which we cannot even see. The smallest particle, which we cannot see our naked eye, but it has a huge amount of energy in it, which we can exploit. And that is by the use of nuclear fission. And we can get a huge amount of energy. So energy is present in those atoms which we cannot see with our naked eye. And energy is also coming from the sun. All of the energy which is available on Earth, directly or indirectly, it is actually coming from sun. So energy is available in atoms which we cannot see, and energy is actually reaching on the surface of this Earth in the form of sun. All those fossil fuels are actually the indirect forms of sun, solar energy. It is the sun energy which is actually goes into the plants, and those plants and other materials which were dumped into the ground, and then it converts into fossil fuels. So actually it is indirect form of solar energy. So all of these energies, we need to convert it from one form to another. For example, chemical energy of the fossil fuels, first we convert it into heat energy, and then this heat energy is converted into mechanical energy and turbines or engines. in turbines or engines. Engines are your automobile engines. Turbines are the devices which is used to produce electrical energy. So you can produce electrical energy from turbines or even from engines. You see the diesel generator in your surroundings, those are actually engines, those are not turbines. Turbines you normally see in the power plants, right? It could be a hydraulic turbine, it could be a steam turbine. So in case of steam turbine and gas turbine, what we are doing, we are converting fossil fuels first into heat, and then this heat is used to derive this turbine. Or in case of engine, it is actually the heat which is deriving the engine. In both turbines and engines, what we are doing, we are converting the chemical energy of the fossil fuel into mechanical, and then this mechanical energy is converted into electrical energy. So there, for example, we can also convert this nuclear energy of uranium atoms into heat, and then again this heat is converted into mechanical energy in turbines or engines. So another example, for here you are converting potential energy of water. In some cases, what we are doing, we are converting the potential energy of water into kinetic energy, and this kinetic energy is used to run the water turbines, and again this turbine is used to produce electrical energy. Another example, kinetic energy of winds is converted into electricity by using a special device which is known as windmills. In windmills, what is happening? This kinetic energy of the wind is converted into, again, mechanical energy, and this mechanical energy is converted into electricity. The device which we are using for this purpose is known as windmills. Similarly, energy of the tidal waves in the sea, right, that can be converted into mechanical energy by using a special type of turbine which are known as floating turbine, and then this turbine is actually producing electricity. Here you see the various energy sources and the possible conversion paths which we see in our surrounding. So this figure actually is showing the various energy sources and the possible conversions. And the most important conversions, or the most common ones, are shown with this solid arrows, right? And the less common conversions are shown with dotted arrows. So what you see here in this diagram, the most useful form of energy for us is either electrical or mechanical, right? So how to get this electrical energy or mechanical energy? So these are the available sources of energies. So for example, we can exploit solar energy. Now this solar energy can be converted directly into electricity using a photovoltaic cell, or this solar energy is first converted into heat, thermal, and then this thermal energy is converted into directly to electricity. There are devices where we can convert heat energy directly to electricity, or in most of the cases, first what we do, we convert this thermal energy into mechanical energy first, and this mechanical energy is converted into electrical energy, right? In, for example, what is the example? Let me draw a figure. But before that, I again want to check if all of you are with me. So all of you are with me. Please respond here again. Because I am using full screen, so that's why I don't know in the background you are with me or not. If you are not with me, you may open your mic and you may tell me, right? Okay, thank you. So we were discussing this figure. So let me give you an example. Solar energy, for example, this is called solar concentrator. Here you have a sun, right? Sun rays are coming. Those are striking this surface. This surface is a reflector, a parabolic shape reflector. What it does, it concentrates this energy. It reflects. It does not absorb the electrical energy. The material of this concentrator type solar collector, what it does, it reflects these solar rays onto a receiver, onto its focal point, because it's a parabolic shape reflector, which converts or which reflects this energy onto a receiver. In this receiver, it's like a pipe in which some fluid is moving, for example, water. So this water gets, it absorbs the heat, this energy, solar energy, which was reflected, and then now it is concentrated onto this receiver. What is this receiver? It is a metal pipe, for example. It's a metal pipe and painted black. So it is painted with black paint. So this black paint will absorb this energy, all of this energy which is reflected from this reflector. So this energy is absorbed by this metal pipe, and when this metal pipe absorbs the solar energy, it converts this electromagnetic radiation of sun into heat, and this heat is then transferred to the fluid which is flowing in this pipe. So this fluid will absorb this heat, and this fluid will, if, for example, if it is water, then the temperature may be up to, you can attain temperatures of around 500 degrees Celsius using such devices. So you can design these devices in such a manner steam out of it. Then this steam, what is this steam? This is actually thermal energy. The energy of the sun, which was in the form of electromagnetic radiation, now it is converted into thermal energy. Now you can take this thermal energy to run a turbine. For example, there is a turbine like this one, and steam is striking this turbine, right? After striking the turbine, steam leaves and it, so it transfers its energy, all of the energy in the form of heat. That's why its temperature was raised to 500 degrees Celsius. Now this energy is transferred to this device, which is called a turbine. So it means this thermal energy is now converted into mechanical energy. Now this turbine is connected to a shaft. This is a rotating shaft. This shaft is rotating. For example, this is a shaft, right? The view into the slide or into this board, this will be a shaft. On the periphery of this shaft, there were such blades on which steam was striking and then steam was leaving. So what it was doing, it was making this shaft to rotate. Now this shaft is rotating inside a magnetic field, right? Inside a magnetic field. So whenever there is a relative motion between a magnet and a conductor, you can get electrical energy from Faraday's law of electromagnetic induction. So what was the purpose? The purpose was to make this shaft to rotate. This is a conductor, and you want to rotate this conductor inside a magnetic field. So you need energy to rotate this shaft, and this energy is actually transferred from sun, but not directly. But first, this energy is converted into heat, and then this heat is converted into mechanical energy by running the shaft, because when this shaft is rotating, so it means we are getting mechanical energy. Something is rotating, something is moving. Now this movement is actually inside a magnetic field. So that's why we get electrical energy. So here is what I have explained, this thing. Sun energy is converted first into thermal, then this thermal energy is converted into mechanical, and this mechanical energy is finally converted into electrical energy, because we want to have our useful form of energy is actually electrical energy, right? Similarly, you can convert solar energy directly to electricity. Similarly, here you have another example. You may use a geothermal source. The core of the earth is very hot, so you may produce that steam. The similar steam which you have produced here using solar energy, you can produce the same steam using geothermal energy. You can make the water to go down into the earth at a very lower level where the temperature is very high, so you can produce steam there. And then this steam can be this conversion of geothermal energy into heat is actually the thermal energy conversion. And again, this thermal energy conversion means this heated steam can be used to make a shaft to rotate inside a steam turbine, and then you can get electricity. Here, the chemical energy of the fossil fuels, all those fuels, oil, coal, gas. Here again, what we are doing, we are converting this chemical energy into thermal energy first, and then this thermal is converted into mechanical using the same phenomena which I have explained here. And this mechanical energy is then converted into electrical energy. Similarly, nuclear energy, in a nuclear fission process, what you are getting energy in the form of heat. And again, this heat can be used to produce steam, just like here. Steam. And this steam can be used to run a turbine where we will get mechanical energy, and this mechanical energy is converted into electrical energy. So in all these cases, what you see, the thermal part is common. All these energies first need to be converted into heat first, and then this heat can be converted directly to electrical energy, but this is not very common. There are certain devices, for example, those are known as Peltier devices or thermoelectric generators, but those are not very common. The common phenomena is this one. First, thermal is converted into mechanical and then electrical. Here you see hydro energy, wind energy, or tidal waves energy. All these energies can be converted into electrical, but there is no thermal part involved here. In case of hydropower plant, wind power plant, or tidal power plant, here what you are doing, you are converting the energy of these various types directly into mechanical energy. You do not convert these energies into first heat and then mechanical. It is directly converted into mechanical and then mechanical to electrical using the same phenomena. You need a movement of the shaft inside a conductor, inside a magnetic field, right? So whenever there will be a relative motion between a conductor and a magnetic field, electrical energy is produced. Okay, in some cases, in some of your devices, what we are doing, we are converting electrical energy into mechanical energy. For example, in your motor, electric motors, the purpose is to convert electrical energy into mechanical energy. And in some cases, you are converting electrical energy into heat energy. The simplest example is your electric resistance heater, which you normally use to heat water in winter or to heat the whole room for space heating during winter season. So what you are doing, you are converting electrical energy into thermal. So it's not always thermal to electrical. It may be electrical to thermal. It's not always mechanical to electrical. Mechanical to electrical energy is you get it from a turbine, but electrical to mechanical energy examples are pumps. What your pump is doing, it is converting electrical energy into mechanical energy, right? Or your fans, what fans are doing, they are also converting electrical energy into mechanical energy of those blades of your fans, and that blades are actually making the air to flow. So in this figure, what you have seen that in all these cases, depending upon our useful output, what we need, it could be an electrical energy, which we need to run our appliance. It could be a thermal energy. In some cases, it could be a mechanical energy. So, but all those energies may not be available naturally, and we have to use other sources of energies, and you have to convert it into your useful form, which in most of the cases is electrical or mechanical, or in some cases it could be thermal energy, right? For example, solar energy can be converted into thermal energy, and this thermal energy can be used to heat the water in the winter season, or it can be used to heat the rooms and buildings during winter season. There are many other devices which are not covered here, but most of the devices in general, those are explained with the help of this. So what is thermodynamics? Thermodynamics, wherever you have this thermal part involved, whenever you want to convert one form of energy into another form using a thermal part in between somewhere, it falls in this heading. This subject is dealing with this energy conversion process which involves thermal. For example, when you convert solar energy directly into electrical energy, it does not involve thermal part, then it is not a thermodynamics. It is an energy conversion process, but it is a different domain. The electrical engineers are dealing with this part when they are converting solar energy directly into electrical energy. But when you want to convert solar energy into thermal first and then into mechanical and then to electrical, then this is thermodynamics. Nuclear to thermal, thermal to electrical or mechanical, this is thermodynamics. This is thermodynamics, right? Similarly, geothermal to thermal. This portion, this is not a pure thermodynamics, because here we are converting this energy directly into mechanical and then from mechanical to electrical. So this part is actually dealing with the fluid mechanics part. You will be studying the course of fluid mechanics. So there you will be studying these devices where you are converting this energy directly into mechanical with no thermal part involved. So whenever there is a thermal part somewhere during any energy conversion process, that is actually the topic of thermodynamics, right? So that gives you a very clear indication, this one particular slide, why there is a need to study this course, because we need to design these devices, we need to manufacture all these devices, but before manufacturing, it must be designed. So how to design these devices, this is the thermodynamics course, which we will try to cover in this semester and also in the next semester. Okay, once again, all of you are with me. Okay. I think we have 10 more minutes, so I will continue. Okay, Ji, thanks. So this slide is covered. So now with the discussion which we have just done, one thing is clear: thermodynamics means therm plus dynamics. So therm means heat, because whenever you are converting one energy into another energy, there is a therm part, heat part. And dynamic simply means power. Power means something is running, either electrically or mechanically. So whenever you are converting heat into power or power into heat, power here means heat is also power, but here when we are using the term power with reference to dynamics, means something is moving. Right. Automobile is moving. Why it is moving? Because you have converted heat into power. Right. Electrical energy is produced in a power plant. Why? Because you have converted somewhere, you have converted heat into power. Right. In electric resistance heater during winter season, what you are doing, you are converting power into heat. Right. In your refrigerator and air conditioners, which we will study later on, again, you are somewhere converting power into heat. So wherever heat to power or power to heat conversion is involved, that is thermodynamics. So we can define thermodynamics in many different ways. So one of the way is to define thermodynamics is the science of energy, which is focusing on energy conversion processes. Which energy conversion processes? Which involve this part, therm. And also in many cases, we want to store energy for later use. So how to store energy in the most efficient way, that is also a part of our topic of thermodynamics. So thermodynamics is a science which is dealing with the energy conversion processes and also energy storage. Another way to define thermodynamics, it is a science of the relations between heat, therm, work, or power, or dynamics. All these mean the same thing. Whenever we say dynamics, something is moving. We may say it is power, something is moving. We may say it is work. So work, power, or dynamics, all are same things in thermodynamics, right? So it means it is a science which is telling us the relationship between heat, work, and now the third important thing is properties of the system. So what is meant by properties of the system? For example, let me use the same example of this sun. and concentrator. Here you had this receiver, solar energy was striking, and it was now focusing on this part. Okay, so what is happening here? Here you are getting heat energy, right? The radiation of the sun is converted into heat, and then this heat is transferred to run a turbine, right? So when this water was heated, what happened to water? Its temperature has changed. For example, initially temperature was 20 degrees Celsius, but now it is increased to, for example, 300 degrees Celsius, right? And for example, the pressure of this water inside this pipe was, for example, 15 bar. Now this steam is now leaving at 300 degrees Celsius. Now it strikes these blades and it leaves at a lower energy because it transfers its energy to this part, which is a turbine, and you get work output. Because something is moving, it means you are getting work or power or dynamic form of energy. So here the heat, which is Q, is converted into work. But during this conversion processes, how we know there is a conversion process is taking place? We know because temperature was increased from 20 to 300 degrees Celsius, right? And for example, pressure was 15 bar. If now when the steam is leaving this turbine, this is a turbine where we get some work output. So when this fluid is leaving, its temperature will drop because energy is taken out of this fluid. Fluid itself is not going out. Fluid is just entering and then leaving. The mass of the fluid is in this direction, but some of its energy is taken out. So its temperature will drop again, for example, to 100 degrees Celsius. When it was entering into this turbine, its temperature was 300. Its pressure was 15 bar. Now its pressure will also drop because energy is taken out. So it, for example, if you measure this pressure of this water, which is leaving this turbine, for example, this pressure is 5 bars, right? So what are these things? 20 degrees Celsius, 30 degrees Celsius, 15 bars, which now changes to 100 degrees Celsius and 5 bars. All these are properties of the system. These are the properties: temperature, pressure, volume, etc., with which you actually guess there is some energy conversion process. So thermodynamics is dealing with not only heat, Q, not only work, W, but also properties of the system, because temperature is changing, pressure is changing. So this is a science of the relations between heat, work, and problem. So this is another way to define thermodynamics. Another way is science of regularities or laws or rules or principles which are governing the process of energy conversion. So how to adopt these interactions to our benefit, that is the main thing. So thermodynamics will tell us how we can get these interactions to our benefit. What are these interactions? Where we are converting one form of energy into another form and we are getting a useful output. This is the useful output for us. But to get this useful output, we have to make such system. जो हमने system यहाँ create किया, that is our task as a mechanical engineer or as a student of thermodynamics, how to design these systems to get this useful output. So how to adopt these interactions. What are these interactions? This energy is converted into heat, then heat is converted into work. So these are various interactions. To our benefit is to get this useful form, because we want to run our appliances using this energy. So thermodynamics enables us to answer this question, how we can adopt these changes. Okay, I think time is almost over.